Hello humans, my name is Professor Leach, and today we want to talk about reading and writing expressions. Specifically, we want to continue talking about reading and writing expressions. We need to remember how operations work, remember how operations interact, and remember that we use parentheses for clarity. That was the lesson from Quiz X. Quiz X was not supposed to point out how dumb we are and how bad the rules are, although that's a fun extra thing to get out of it. It's to point out that there is a better way to write the expression, depending on what we mean, with parentheses, and so we should do that. We need to express things clearly, especially if it's going to matter on something like a quiz or a test or something where points are at stake. If it's just in casual conversation with your friends, then it won't really matter. But when points are at stake, parentheses for clarity. And that's the responsibility of the person assigning the points, not you as a reader. So how operations work and how operations interact. What I'm referring to here is addition, multiplication, and exponents. We only add things that are the same, and when we add them, it doesn't change what they are. Multiplication is repeated addition. Multiplication goes before addition unless there are parentheses. If there are parentheses, multiplication distributes over addition. Exponents represent repeated multiplication. Exponents go before multiplication unless there are parentheses. If there are parentheses, exponents distribute over multiplication. It's those last ones that I really want to emphasize today. Because a lot of times we see this terrible representation of what I was just talking about. We call this the distributive property, and then we write these symbols. A parentheses B plus C close parentheses equals AB plus AC. And we try to summarize with this equation the fact that multiplication distributes over addition. The problem comes about is that we leave off that what makes this go is the multiplication, not the parentheses. This is an expression that's telling us that multiplication distributes over addition. This means that multiplication, A times B plus C, is equal to A times B plus A times C. It's the multiplication that makes this go. Multiplication distributes over addition. Multiplication distributes over addition. It's the multiplication that makes this happen, not the parentheses. It's the multiplication that makes this happen. It's the multiplication that makes this happen, not the parentheses. It's the multiplication that makes this happen, not just the presence of parentheses, because parentheses are not an operation unto themselves. It's just grouping things together. So that's why instead of saying distributive property, I say multiplication distributes over addition unless there are parentheses, or sorry, I say multiplication goes before addition unless there are parentheses, and if there are parentheses, multiplication distributes over addition. Any questions? It seems that I'm being very picky with the language, but that's only because I'm being very picky with the language, because math is a very picky language to write. Here's the reason that we care about this. We don't want to think that it's just the presence of parentheses that allows us to distribute things, because there are a lot of operations that don't distribute over addition, like all the other ones. So exponents do not distribute over addition. Exponents do not distribute over addition. If I have an expression that says, say, x plus y squared, this means an x plus y times another x plus y. We cannot just square the x and square the y. So this we would have to multiply it all out with more distributive property because now it's multiplication. And now multiplication distributes over addition. So this is going to be x squared plus xy plus another xy plus y squared. And we only add things that are the same. And when we add them, it doesn't change what they are. So x squared plus 2 copies of xy added together plus a y squared. We can't just distribute the exponents over the sum. Exponents do not distribute over addition. So x plus y, the square of the sum of x and y, is the product of 2 copies of the sum of x and y, not just x squared plus y squared. I can't just take the 2 and distribute it to the x and y. That's not what this means. Now, we're not doing this because these are some funky rules that we decided to come up with to torture future algebra students. That's just a side benefit, or I mean a side effect. That's just a side effect. This is just not how numbers work. We can't just square each digit of a number. So this right here, the reason that it's not x squared plus y squared is because that's not how numbers work. So if I have, say, 25 squared, that means 25 times 25. That means I need to take 25 times another 25. 5 times 5 is 25. 5 times 20 is 100. 20 times 5 is 100. 20 times 20 is 400. I don't know why I confused myself at that point. So I have 400, 200, and 25, otherwise known as 625. So we would multiply these in the same by using the distributive property. I would distribute each digit of one number over every digit of the other number. So I'd have the 400 plus 100 plus 100 plus 25, or 625. We would probably do this in some weird order because I'd put the 5 here and carry the 2, and then 100, and it's just weird. You know how I feel about that. But that's not how numbers work. We can't just look at 25 squared and say 25 squared is 20 and 5 squared, and so that's 20 squared plus 5 squared, so that's 425. That's not how numbers work. We're not doing this because we want to come up with some weirdo set of rules. That's not how numbers work. Exponents do not distribute over addition. Multiplication is what distributes over addition. So I don't like saying things like the distributive property. I think that's a terrible way to phrase this concept. I do not like to write a parentheses b plus c equals ab plus ac until we understand that this is a representation of multiplication distributing over addition. And it's the multiplication that makes this happen, not the parentheses. We're going to learn lots of different functions, and it's really critical that we don't just read the form of parentheses and say, oh, we distribute because parentheses. It's not the parentheses that makes this happen. It's the multiplication combined with the parentheses. The combination of those things. Any questions? Today I want to bring up another place that we see this distributive property in action, sometimes going the other direction. We also see the distributive property show up in adding fractions. We can also think of the distributive property as showing up in fractions. Here's what I mean. So we know that if we want to add a couple of fractions, we need to have a common denominator. So if I have 3/7 and I want to add 2/7, we know we get 5/7 because what we do is add the 3 and the 2 over the common denominator of 7. Here, we add things that are the same, and when we add them, it doesn't change what they are. The way we can think of this as that the 3/7 plus 2/7 is a 3 plus 2 all over 7. So if we think of this in reverse, we could think of distributing a 1/7 to the 3 and the 2. This is a really weird way to look at things, and this is not a way to do the problem because we've already got the answer. It's 5/7. We're done with the finding of the answer part. What we're not done with is connecting this to other ideas. So we know that the answer is 5/7. That's not the issue. 5, right? 3, 4, yeah, 5. We know that the answer is 5/7, but we want to think about this in different ways. So this is 3 plus 2 divided by 7. It's the sum of 3 plus 2, and it's all divided by 7, which is the same thing as multiplying by 1/7. Dividing by 7 is multiplying by 1/7. That's just understanding our operations, how multiplication and division are connected. Dividing by 7 is the same as multiplying by 1/7. Dividing by 7 is multiplying by 1/7. That's because 7 and 1/7 are reciprocals. So dividing by 1 is multiplying by the other. And in this way, we're dealing with multiplication. Now that this is multiplication, I can think about distributing the 1/7 to the 3 and the 2. And so it's 1/7 of 3 and 1/7 of 2. So this multiplication distributes over addition. And that means since division is following the same rules as multiplication, that division should distribute over addition as well. Once again, this is not progress on coming up with the 5/7. If the problem is to come up with 5/7 quickly, then doing this by hand is the wrong way anyway. It's like, well, hey, I can help you come up with answers quickly if that's the goal. Then I'm like, oh, that's not the goal, calculator. Get out of here. We're trying to learn stuff. It's like, oh, okay. I'm just kidding. The calculator is not offended. I removed the calculator as being offended chip, so it won't get offended when I make fun of it. I put it back after class, and then I erase its memory so it doesn't know that I did that thing to it. You know what I mean? So we want to be able to see what's going on. Coming up with 5/7 is the last thing that we care about. We want to understand that multiplication distributes over addition. We want to understand that the parentheses are not what makes this go. It's the multiplication that makes this go. Any questions? Comments? Exponents do not distribute over addition, but we do have that exponents distribute over multiplication. So if we take everything up a level, we do have that exponents distribute over multiplication. So if I have, say, x times y to the n, I can write this as x to the n times y to the n. Exponents go before multiplication unless there are parentheses. If there are parentheses, then exponents distribute over multiplication. So here, it's like I'm distributing this to the n over the product. I can do this because exponents distribute over multiplication. So this only works because what's inside the parentheses is multiplication. Oops, not nullification, multiplication. That's why we get to do this. This is usually referred to as properties of exponents. So we lose this connection about what it means. And which is why I take us all the way back to operations for this class. So we could take all these things that we may have learned as properties of exponents and see them in new contexts as this is just how operations behave. In this regard, it's really important that we read properly where that exponent sits. Is that exponent inside with the y or outside and applying to the entire parentheses, or the entire expression in the parentheses? Because the exponent only applies to what's right next to it. So the exponent only applies to what it's the subscript of, to whatever's right to the left, to the thing on the left. The exponent only applies to the thing on its left. So if I write, say, 3x squared, this means 3 times x times x. Square the x, then multiply by 3. That's what 3x squared means. Square the x, square the x, then multiply by 3. Just like our language that we've been trying, our shorthand that we've been trying to learn. Square the x, so to the second power, then multiply by 3. Multiply by 3. If I don't want that to happen, you'll say, oh, no, that's not what I meant. I want you to multiply by the 3 first and then square the result. Then I would have to write 3x squared. The thing on its left of the 2 is the parentheses. And so now the exponent applies to the parentheses. So this means write 2 copies of 3x. Because multiplication is repeated addition. Sorry. Exponents is repeated multiplication. I don't want to go through the whole list. So in this one, we can square the x. We want to multiply by 3 first. Then square. So first we multiply by 3, then we square the result. If we were reading these things, we read these expressions in English very badly. We would say 3x squared, and that's how we would read the first one. We're lucky in that one because it's 3x squared. We just get to spell it. And the way we speak it is the way we spell it. Those two things match, and that always makes life easier. But the second one, we might be tempted to just say 3x squared. And some people think, like, oh, we should leave a bigger pause. 3x squared, or 3x all squared, or some other variation of that terrible language. But if we really want to be clear about it, it's the square of the product of 3 and x, or the square of the product of 3 and x. I think I said the same thing twice. That'd be the best way to say it. We want to work on how we can say things so that they are perfectly clear. We can't even, in this case, say the square of 3 times x, because that might be just square the 3 and then multiply by x. Or how do you want us to do that? Any questions? All right. So it's important to understand and be able to read these expressions, because sometimes we will want to simplify the expression. And so in certain scenarios, it might be useful to have this 9x squared. Any questions? All right. So this is all kind of review and reinforcement of things that we've already talked about. I have a page, I finally have a page of examples on simplifying expressions, where it really, and it's important not just to look at the expressions and their simplified forms. It's important to read the way that I want you to read these expressions. So I have one where I have in parentheses 5x cubed y, and then I want all that raised to the second power, and how we read that. Not just square all this stuff inside, even though we can just distribute the square. We want to read what that means so that we apply the rules properly. There's also our summarization of how we think about operations, wherein we only add things that are the same, and when we add them, it doesn't change what they are. Multiplication is repeated addition. Multiplication goes before addition unless parentheses. If there are parentheses, multiplication distributes over addition. Exponents represent repeated multiplication. Exponents go before multiplication unless parentheses. Exponent, if there are parentheses, then exponents distribute over multiplication. It's a lot less catchy than PEMDAS, but it represents how we want to think about the operations and not just robotically follow the rules, because how we follow the rules that we've written are not what we do anyway, which means they're trash rules. Like speed limits. 65 miles per hour is trash. It's a lie. Because I could be driving 70 miles per hour down 280 and get passed by a police officer who is ostensibly there to keep me from going over the speed limit. It's not a limit. It's just arbitrarily applied, and any rule that's arbitrarily applied shouldn't be a rule. Or we need to stop applying it. Either rewrite the rule and apply it, or just get rid of it, because we're not really doing that anyway. You know what I mean? All right. Here is the next phase of simplifying expressions. We might have seen things like square roots. And so I'm going to write that down. Square roots. I'm just going to write it down. No, I'm going to do an example. So we know some square roots. I'm guessing. This is a guess. We know some square roots. If I asked y'all, type in the chat, what is the square root of 9? Awesome. 3. The square root of 9 is equal to 3. So this is the square root of 9 is 3. Why is that? Why is the square root of 9 3? What do we do to 3 to turn it into a 9? Three times 3, or 3 squared, we know a lot of what are called perfect squares. Square root of 9 is 3. What's the square roots of 16? 4, because 4 squared is equal to 16. What's the square root of 25? 5, because 5 squared is 25. Square root is the inverse of a square. Just like division is the inverse of multiplication, and subtraction is the inverse of addition. I forgot the word for a second there. So a square root is the inverse of a square. So a square root is an inverse of a second power. If I told you that smiley face squared, nonplussed face squared is equal to happy face, then what do we know? That one's just too hard to write, so I'm just going to say it. That would mean that the square root of happy face is equal to nonplussed face. Because if something squared is equal to happy face, then the square root of happy face is that something. That's how squares and square roots work. Any questions? Is anybody who's never seen square roots before? Usually we see them and it's pretty common, and we just get them as these weird things. There are square roots of other numbers. We get these nice ones because I picked very specifically 9, 16, 25. Other ones I might pick are 36, 49, 64, 81, 100, 121, 144, and so on. The so-called perfect squares. If we have the square root of a non-perfect square, that's an irrational number. It's a decimal that goes on forever without repeating. So the square roots of a non-perfect square is irrational. Irrational means we can't write it as a fraction. It's irrational. Rational just means we can write it as a fraction. Irrational is not that. So the square root of a non-perfect square, like the square root of 10, is an irrational number. Square root of 11, square root of 12, square root of 13, square root of 14, square root of 15, square root, all those square roots are irrational because we're taking the square root of a non-perfect square. What that means, it's not a fraction. It can't be written as a fraction. Rational means it can be written as a fraction. So irrational means it can't be written as a fraction. That means its decimal form neither repeats nor terminates. Rational means we can write it as a fraction. Irrational means we cannot. What that means in the decimal form is that the decimal form doesn't repeat or terminate. So 0.5 is rational because 0.5 is equal to 1/2. The decimal terminates at 0.5. I should write leading 0 to make it clear. 0.3 repeating. Here's a decimal form that's repeating, and I can write it as a fraction. That's 1/3. Here's a repeating decimal, 0.3 repeating, and here's 0.5, that's a terminating decimal. But the square root of 7 is irrational It's the square root of a not perfect square. So that's what irrational means in a mathematical sense. I can't write it. It means we can't write it as a fraction. Not that we don't know what the fraction is. It means it can't be done. No one can do it. Not that we just don't know how. Looking in a mirror. Yeah. That goes on forever, but it's essentially repeating. It's getting smaller, but it's a repeating. So in a sense, that's rational. Irrational, it goes on forever, but everybody looks different. That's weird. So irrational means the decimal never repeats or terminates. Terminates just means it stops. So the mirror, well, that doesn't terminate. The mirror just keeps going on forever. But the mirror does repeat. It's just showing you the same picture over and over and over again. So sometimes there's like a lot of digits that repeat. So 1/7, wrong button. If we look at 1/7, it's 0.142857, 142857, 142857. It's just got 6 decimals that are repeating. I don't know how many it carries. 0.142857. It just goes on. It's repeating that same sequence of digits. But the square root of 7, that's just going to go on forever. If I subtract, well, I'm going to run out of digits too fast. These digits go on forever and never repeat. So it's not like it's going to be 0.65, 645751311, 645751311. It's not going to do that. It's not going to repeat. If it does repeat, we can write it as a fraction. If it doesn't, we cannot. And that's what an irrational is. So that's a little reminder about what an irrational number is. That's a lot of terminology. What we really need to notice is that square roots are inverses of squares. And here's the important thing, the one new thing that you get for today. Square roots are 1/2 exponents. Square roots are 1/2 exponents. So if I take 9 to the 1/2 power, that's 3. 9 to the 1/2 power is 3. 16 to the 1/2 power is 4. 25 to the 1/2 power is 5. And my calculator agrees. 9, oops, although I have to ask it the right question. 9 to the 1/2 power, 3. 16 to the 1/2 power, 4. 25 to the, lazy, 1/2 power, 5. Square root is the inverse of a square. Square roots are 1/2 exponents. Square roots are 1/2 exponents. Here's why I care about pointing this out. We've stated our operations with addition in terms of addition, multiplication, and exponents. Those are the 3 things that I keep listing: addition, multiplication, and exponents. Then we just put subtraction in with addition. We just say subtraction is just addition of opposites. Subtraction is the inverse of addition. Division is multiplication by reciprocals. Division is the inverse of multiplication. Square roots are the inverses of second powers. So we're going to look at different kinds of roots, and we're just going to list them as fraction exponents. And that's the big news for today. Square roots are 1/2 exponents. Big thing to walk away from this whole class is that PEMDAS is trash. The big thing to walk away with from today is that square roots are 1/2 exponents. So when you see a square roots, think of it as a 1/2 exponent. Any questions? Comments? Snide remarks? All right, there's going to be a quiz that shows up that exploits this knowledge, that square roots are 1/2 exponents. And we're going to want to make sure that we're just integrating this into the things that we already think about operations. Addition, multiplication, and exponents. This is just adding to that exponents bullet point. Any questions? Comments? Snide remarks? Awesome. So apart from that, I believe that's it. I'm done. Email this to your grandma, and I'll see you some other time.